Welcome back. Can you hear me? Welcome back, everyone, for the afternoon session. Our first speaker is Professor Winnie Lee, and she will be talking about hypergeometric functions, Galois representations, and modular functions.
I repeat all my. It's a great honor and a pleasure for me to attend this conference in honor of my good friend Ram Murthy. I would like to thank the organizers for the invitation. So I first met Ram when he was a graduate student at MIT, and so I really appreciate our friendship throughout the years. And I would also like to thank the support he has offered to me from time to time. And I wish him a happy birthday and many happy and healthy years to come. So today I'll talk about hypergeometric functions, Galois representations, and modular forms. So hypergeometric functions were first introduced by Euler, and Gauss was one who started a systematic study of that. So let me start by introducing the nfn-1 hypergeometric function. Okay. So it's defined, to define it, we have two sets of parameters. The first set is a1 up to an, the second set b1 up to bn, and b1 is always equal to 1. So they are complex numbers. So using them, we define a power series in the complex number z. And the coefficient of z to the r is defined using the Poke-hammer symbol. Here, a parenthesis r is a times a plus 1 times all the way to a plus r minus 1. For instance, 1 parenthesis r is r factorial. So a faster way to express that is gamma of a plus r over gamma a. Okay. So this function is defined whenever the series converges. Okay. And Riemann studied the hypergeometric functions from the viewpoint of differential equations. Okay. And this nfn-1 satisfies an nth order linear ordinary differential equation, and with 3 regular singular points, which we normalize at 0, 1, and infinity. Okay. So now, if I take a non-singular point, and through that point, we know that the solutions passing through that point form the n-dimensional vector space. So we put that vector space at this point, then we collect all these solutions. So then this way we obtain the sheaf over the curve, which is P1C minus 0, 1, infinity. This is the so-called local system of rank n. So now let's take a non-singular point, and we have a cycle in P1C minus 3 points. So then I look at the fiber at this point. I just pick up any solution. Then I move this solution along this curve. When I return to this point, I reach at another solution which may or may not agree with the one that I started with. So we can think that this loop gives us a map which sends a starting solution to the ending solution. So this is a so-called monogeometry representation of the fundamental group of the P1C with the 3 points removed. Okay, so this is the story of the hypergeometric functions over the complex numbers. Or you can think about this is the story of hypergeometric functions on the analytic side. Now, there's also another story of hypergeometric functions on the edge break side. So to do that, we need a further restriction. So we first restrictions that I want the parameters, I want the parameters AI and the BJ to be non-zero rational numbers. Okay. And I would also further assume that the difference between A and the BJ are not integers. Okay. So this kind of I forgot to say, sorry. I should have said that I collect the parameters A1 to up to AN in one set, which I called alpha, and the B1 up to Bn in the second set, which I called beta, and alpha and beta together is a hypergeometric datum. So then to get the edge break side of the story, I want the parameters AI and the BJ to be non-zero rational numbers, and I assume that the AI minus BJs are not integers, so we call this hypergeometric datum primitive. Okay. So with these rational numbers, I look at the denominators, find the least common denominator, we call that M, and we denote it by M, and we regard M as the level of this hypergeometric datum. Okay. So now corresponding to what happened on the complex side, now we have the similar thing happening on the edge break side. So on the complex side, we have this rank n local systems. Now on the edge break side, for each prime L, Katz has introduced an L-adic rank n hypergeometric sheaf. So that's a sheaf correspondence. And before, the curve was projecting line with 3 points removed. Now the curve is a GM, so which is the multiplicity group of the field. You can think of that as a projecting line with 2 points removed, 0 and infinity removed. So they are very similar. And on the complex side, before we have the action of the monodromic group. Now, corresponding to that, we have the action of the Galois group. And it is a Galois group from Q bar all the way down to the cyclotomic field, joining M through the 1. Okay. So for instance, if we look at the action of a Galois group at a fiber, this fiber at a point, which is a non-zero point of the cyclotomic field of Q joining zeta M. And so to describe this Galois action, we will talk about what is the Frobenius trace. And the Frobenius traces, in this case, are known explicitly, is given by the hypergeometric character sums. And this hypergeometric character sums are the finite field analog of the complex counterpart, that is NF and n-1 of the datum at lambda. The point lambda. Okay. So this was first studied, this kind of hypergeometric character sums over the finite field analog. They were first studied by Katz. And a recent memoir written by Fuselier, Long, Ramakrishna, Swisher, and the two, gave a lot more detailed information and the development about this hypergeometric character sums. Later on, we are going to see some example, and I will talk about more about this. Okay. So before I go further, I would also want to point out that there's some differences between algebraic side and the complex side. First of all, the Galois representation only depends on this AI and the BJ modular integers. Okay. And secondly, when we look at the NF n-1 definition, it does not matter how this AIs, the order of AIs, and doesn't matter the orders of BJs. But for the representations, the order matters. If I permute these AIs and BJs, I would have resulting representation differ by twist by character. On the other hand, if I bundle the A's and Bj's in the column vector, like A1, A1, B1, A2, B2, etc., if I permute the column vectors, then the resulting representations are the same. So now, if I look at these column vectors modulo z, so I think about the Galois representations, I look at these column vectors modulo z. Now, we will say that this datum is defined over Q. If I multiply these column vectors by integers co-prime to m, I only end up permuting these column vectors, so the whole set remains the same. When this happens, we say that the datum is defined over Q. When datum is defined over Q, then the Galois representation originally was for the representation of absolute Galois group with until the cyclotomic field joining m to the 1 now can be extended further all the way down to Q. Okay. So there are several extensions. There's one extension which was studied by Boykers, Cohen, and Malit, which I'm going to call that a BCM representation. Okay. So for that particular extension, well, one knows the Frobenius traces explicitly, and they are also given by hypergeometric character sums, which I know by HP, the datum, okay, and the point lambda. For instance, when P is come to 1 modulo the level M, this hypergeometric character sums, we will see that it's very analogous to its complex counterpart. Okay. So first of all, this the finite field analog hypergeometric character sums, they are sum over the characters, the multiplicity characters of the field Fp. So we know that the multiplicity characters form a cyclic group, so we randomly pick up a generator, say omega, and all the characters will be powers of omega. So here, omega to the r, evaluated lambda here corresponds to the z to the r before. And before that, we used to have the product of Pokehammers of the Pokehammer symbols of the AIs and over Pokehammer symbols of BJs on the numerator and the denominator. And recall that each Pokehammer symbol is a quotient of 2 gamma, the gamma of A plus R over gamma A. So the finite field analog of the gamma function is gamma Gauss sum. Okay, so I'm going to replace this gamma by Gauss sums. Sorry. Okay. So here's the coefficient in front, omega to the r. So the product from 1 to n. So now we look at this Gauss sum, the first one over the Gauss sum at the bottom here. So you can think of this as aj plus r over aj. So that corresponds to a parenthesis r, aj parenthesis r. Then that thing should be divided by bj parenthesis r, but we use the Gauss sum identity. So here I have the bj parenthesis r is bj plus r over bj. So originally the b should be in the denominator with omega power. Then I use the Gauss sum identity. I express it using the conjugate. So it's an inverse character. So I put it on the numerator. So that's exactly the finite field analog of the complex counterpart. Okay. So this expression holds for p count 1 modulo m. Remember, this is a rational number. Okay. This is why we have this to make it an integer exponent. Yeah. So I'm a little confused about orientation. Okay. So now I said that a BCM representation has a Galois trace, Frobenius traces given by the hypergeometric character sums. So here it is. So for this BCM representation, as a trace at Frobenius P is given by this hypergeometric character sum, except that in the actual representations, if the fiber at lambda here, then the character sum side is at 1 over lambda, okay? And the difference between the actual trace and the hypergeometric character sums, well, has two parts in front. One part is the sign, and one knows the sign when it's plus, when it's minus. That's explicitly determined by the hypergeometric datum. And the powers of P here also depends on that. So the P part here depends on the how many integer entries that BJs have. Okay, so the bottom line is that after we multiply it all out, the BCM representation has Frobenius trace is always an integer. It's very nice. Okay. So now let me give you one example. Let's take a simplest example. Alpha is a half-half, beta is 1-1. Okay. So this datum is primitive and it's defined over Q, and the level is equal to 2. So in this case, the Q joining -1 the same as Q. So in this case, the BCM representation agrees with the CAS representation, so there's no extension. Okay. So the hypergeometric character sum HP at lambda is given explicitly as this sum over the elements in FP. So phi p here is a quadratic character of the field FP. Okay. And it's evaluated as at a cubic polynomial in X. And the Frobenius trace of BCM representation is exactly equal to the hypergeometric character sum. So very concrete. So now let's see, what is this BCM representation? Okay.
So this hypergeometric series would be related to the monogamy representation of the Riemann surface function that is in the family, or?
It's just simpler. It's related to elliptic curves.
Is that one?
Yeah, it is that one. Because we have quadratic characters, so when lambda is not equal to 1, we look at this cubic polynomial. It doesn't have repeated roots. So y squared equal to this polynomial gives us a Legendre elliptic curve. And when we count the number of solutions of this elliptic curve over FP, well, you know that non-trivial part is given by that character. So this sum is nothing but the AP of this elliptic curve. Okay. So this tells us that the Frobenius trace of this BCM representation is equal to the AP of that elliptic curve. So that tells us that this representation is precisely the Tate module of this elliptic curve. So in particular, we know that this BCM representation is modular. It comes from this elliptic curve. And when lambda is equal to 1 here, the sum is equal to 1. Okay, so the representation is one-dimensional. I think I went too fast. I talk about the Frobenius traces. There's another conclusion I should have mentioned. That is the degree of the representation. Okay, so when lambda is not equal to 1, the degree is equal to the length is equal to n. Okay. When lambda is equal to 1, the degree drops by 1. So it's some degeneration, degree drops of 1. So then let's go back and look at these examples here. When lambda is not equal to 1, the BCM representation is degree 2. This is the Tate module. And lambda equal to 1 is degree 1. And because the trace is equal to 1, so it's a trivial representation. So now we have seen that to the the hypergeometric datum. So we have a complex side, we have an algebraic side. On the complex side, we have the representation of the monotomic group. We have the monotomic representation of the fundamental group. On the algebraic side, we have representation of the Galois group. So what's the relationship between this Galois group and fundamental group? Okay, so it turns out that they are related by the fundamental group, the so-called état fundamental group of the curve, which is a projected line minus the 3 points, well, at a generic point. Okay. More precisely, the Galois group is a quotient of this état fundamental group, and the kernel is the profinite completion of the pi 1. It's the fundamental group. So these are the two, the way these two groups are related. And we are going to explore these relations, okay? So I have 10 minutes. Okay, so I would like to talk about computing the traces of Heck operators. Okay, so this is joint work with Bill Hoffman, Ling Long, and Fountain Tu. Okay. So we are interested in giving an explicit formula for the traces of Heck operators on the space of K+2, say cusforms for the group gamma. Okay. And this gamma is a congruent subgroup of SL2R, okay, such that the corresponding the curve of half-plane modular gamma is either elliptic modular, okay, or a Shimura curve defined over Q and of genus 0. Okay. So when the group is elliptic modular, then we are talking about cusforms. When the group, when the curve is a Shimura curve, there's no cusp, then this notation just means that all the modular forms. Okay. And of course, if the group contains minus identity, we only talk about even weight forms. Okay. So this question of computing the trace of Heck operators on the whole space was previously considered. So Agron had a result for gamma naught 4, Agron Ono for gamma naught 8. Fréchet, Ono, Papanikolas did it for the new forms for gamma naught 8. And Ihara and the independently Fuselier did it for SO2Z. And Nennen did it for gamma naught 3 and gamma naught 9. So this were all computed group by group, and they all use the Selberg trace formula. So what I'm going to do is to express this trace of Heck operators in terms of the hypergeometric character sums. So, and we are going to give a uniform approach, not group by group. Okay. So our idea is to take the geometric approach. Okay. So we think about this famous theorem by Deligne. So when the group is gamma is the familiar elliptic modular group, then Deligne says that the trace of a Heck operator on the space of K+2, weight K+2 cusforms is equal to the trace of Frobenius on the first état cohomology of the modular curve with the coefficient in a sheaf. So this sheaf, I call that automorphic sheaf. So this, and so this is for elliptic modular case. For the case that the base curve is a Shimura curve, and Ota did a similar thing. Okay. So let me say a few words about this sheaf. Okay. So this sheaf was first introduced for the group which is torsion-free. So in this case, that it's defined using the universal elliptic curves. Okay. And for the case of Shimura curves, it's defined using the universal abelian surfaces with a quaternion multiplication. Then if the group gamma has torsion points, then Well, we just take the sheaf from the subgroup without torsion points, then we do the push forward. Okay. So this is how it's done. Okay. A nice thing about this geometric expression of the trace of Heck operators is that there's the Lefschetz fixed point theorem, which expresses the trace of Heck operators in terms of finite sum. So it becomes the Frobenius trace at the points of the curve over finite field Fp. So what this really means is that if you take any finite field of, take any point of the curve over Fp, you just go back to the original curve to find the point from which that point gives this lambda. You look at that fiber, then you look at action of Frobenius at P at that fiber, and that trace is this trace. So this is a very beautiful formula, except that one doesn't know how to compute the trace of Frobenius. On the other hand, I just started by telling you that there's another very nice sheaf. We know all about Frobenius trace. That's when that sheaf is coming from hypergeometric data. Okay. So the idea is to try to connect the two. Okay. And before doing that, I would also like to remark that for the automorphic sheaf, all we need to know is the what happens at the base. Say if the group, the first case, when the group gamma contains minus identity, then we have only consider the even weights. So that means that I need to know what happens for V2. And if gamma doesn't contain the minus identity, then we need to know what happened to V1. So if we know how to replace V2 and the V1 by what we know, then for the rest, basically it's taking symmetric powers. So our idea is to replace V2 or V1 by a hypergeometric sheaf if we can. Okay. If it doesn't work, then let's see whether we can twist it by a character so that it would work. Okay. Now, suppose we have our targeted hypergeometric datum. So we have this hypergeometric sheaf. I want to say that this hypergeometric sheaf has what I want. Okay, I compare that hypergeometric sheaf with V2 and V1. So I want to say that they are the same. If not, what kind of twist do I need? So I need to compare them. So to compare them, we first to see what happens to the complex side. So there we use the Katz's rigidity theorem. So we compare the complex side to find, say, what kind of twist is needed to fix the complex side. And then the general comparison theorem tells that after the complex sides match, the l-adic side, the algebraic side, differ by a character of finite order. And to determine that character, it suffices to see what happens at any stock of convenience. So that's the idea. Okay. So it's all very nice. If we can do this, then we can compute. But this method also has its restriction because we want to use the hypergeometric sheaf. If you remember, the hypergeometric sheaf is defined on projected line with 3 points removed. That means first restriction is that our modular curve should have genus 0 first. Second, it should be defined over Q. And 3, it only can have 3 bad points. By bad points, I mean the curves together with elliptic points. And these 3 bad points have to be Q rational because they have coordinates 0, 1, infinity. Okay, so these are the constraints. So then we search over all the possibilities. We find that there are exactly 7 groups which fits that requirement. Here they are. Okay. So for instance, there's a 2, 3 infinity. It tells you this group has 2 elliptic points. One has order 2, one has order 3, and it has 1 cusp. Okay, so that group certainly is SO2Z. Okay. So among all the 7 groups, you see that 6 groups has infinity, it has cusp, so they are related to elliptic modular groups. So we see the familiar groups, and here the plus groups means that gamma naught 2 together with the Atkin-Lehner operator, likewise for gamma naught 3. So there's only one group, 2, 4, 6, which doesn't have infinity, so this one comes from Shimura curve. Okay. So I also listed that corresponding to hypergeometric datum. Okay. So let me say a few words about this group 246. So this 246 comes from the indefinite quaternion algebra over Q with discriminant 6. Okay. So this quaternion algebra has only one maximum order of 2 conjugation, which we'll call the OB. And in that maximum order, we pick up the norm 1 elements. So they correspond to the SO2Z on the elliptic modular side. Okay. And the 246 is this group, OB1, together with the Atkin-Lehner operators, all the Atkin-Lehner operators. So it is a plus group, so to speak. Okay. So now let me explain. I'm done. Well, I explain our results. Okay. So for the last 5 groups, they all contain minus identity. So we only consider even weight forms. Okay. And we can see that the contribution at the points, the generic point, is given in terms of the hypergeometric character sums. And from the elliptic points, it's coming from the hypergeometric character sum at the lambda equal to 1, or they are explicit Jacobi sums. And each cusp will contribute 1. Okay. And the first 2 groups, they do not contain minus identity. For the even weight forms, it's the same expression. For the odd weight case, that we'll find that the trace is equal to 0 if this prime p is come to 1, modulo congruent to -1, modulo the level 4 or 3. When p is come to 1, modulo the level, and the contribution at a generic point and the elliptic points are similar, but one has to be careful about the contribution from the cusps. So at the regular cusp, contribution is 1. At the irregular point, contribution is -1. The group gamma 1, 4 does have 1 irregular cusp. So here's one example for 246. Okay. And the first case that we have a non-trivial form is when weight is 8. Okay. In this case, it's 1-dimensional. So, and I have to stress that when we consider the modular forms on the Shimura curves, one can define Hecker operator the same way as before, but the forms no longer have Fourier expansion. So there's no way to describe the Hecker operator explicitly like we did in the past on the Fourier coefficients. Okay. So actually, it's very difficult to compute the Hecker eigenvalues. But here we have a very explicit expression of the Hecker eigenvalues for all the prime p from 7 on. Okay. So we first describe what's the contribution at the V2. Okay, so you can see it's a hypergeometric sum together with the thing in front is the twist that we found. Okay, and the actual contribution is because of the symmetric power, so it's a cubic polynomial in terms of the value which is found there. And the second line is a contribution from the 3 elliptic points. So let me end by a few remarks. Sorry for go over time. So the first is that, so say if I look at the 246, okay, this is 1-dimensional. And for Frobenius, the trace of a Hecker operator gives you the eigenvalue of trace. What if we are in the case that space has dimension higher than, greater than 1, then we can still get a operator eigenvalues by computing Frobenius p squared, cubed, etc. Okay, if you do enough, then you will get it. And second, we see that this method, we started with only 7 groups. What happens if my group is not one of them? But if you have a subgroup of one of them, so the gamma prime, so then the modular curve x gamma prime is a cover of the curve x gamma. If that modular curve for gamma prime is defined over Q, if you have the explicit projection map, then you can pull the sheaf of x gamma back to x gamma prime and to get a Pekka trace or x gamma prime. Okay. And the third application is that we can get an explicit value of the hypergeometric functions. Okay. And the fourth is a very interesting byproduct, is that if I look at what happens to the Ramanujan tau function, it's one-dimensional. Okay. And we found out that this tau p has the following congruences modulo 10. And turns out that this was quite well known among the people who do the partitions. And for instance, the Swinton-Dyer has this proof using Galois representations. And we get this congruence just from the hypergeometric character sum computation. Okay, so I stop here. Thank you very much.
So any questions, comments? Yes, Sunil.
The last one?
Last digit of tau p modulo 10.
Which one?
In the tau p modulo 10,
Modular 10?
the 4 is missing, and also it is not equidistributed among the physics classes more. Is there any reason, like special reason for?
You mean, what if 4 is
Well, he
missing?
says the residue
For-
class 4 is not one of the values taken on by tau p modulo 10. So it means that tau p is not equidistributed mod 10.
Ah,
And so
yeah,
he's asking, is there an explanation for that?
I see. Yeah, okay, now I understand.
So any more questions, comments? Okay. So any more questions, comments? If not, let us thank the speaker again.
Thank you.
We meet in 5 minutes.